welcome. So, we are discussing in the module 10 the thermoelasticity. So, in the last class what we have derived essentially is what is the form for uncoupled thermoelasticity, and specifically the Duhamel-Newman relation for the thermoelastic material. So, the essentially the stress strain relation and we have discussed in terms of the strain energy, which is not only dependent on strain, now it is dependent on the temperature also. So, this we have discussed in the previous lecture. So, now we know what are the thermoelastic deformation, that is for an uncoupled formulation, what are the thermoelastic deformation, and what are the stress strain relationship we know in terms of Duhamel relation. So, we know the thermoelastic relation, for instance the strain displacement relation, and then we know the strain compatibility equation, which is we studied earlier. For instance, in a two-dimensional case, we know what is the strain compatibility equation. We also know the equilibrium equation. Here I am describing the body force in terms of F. So, and then the Duhamel-Newman constitutive equation. In the constitutive equation, we have this form. This is the mechanical stress, and this is the thermal stress part. And so, now here the basic idea is your you have the additional material constant for a thermoelastic material, which is the coefficient of thermal expansion of solid, which is denoted in terms of alpha. And this relation is for isotropic material, but for an anisotropic material in different direction, coefficient of thermal expansion can be different. For instance, alpha x in the x direction, alpha y in the y direction, alpha z in the z direction. This is possible. Certainly, this will be then a diagonal matrix. So, instead of a single coefficient alpha. Now, for an energy equation, that also we have seen in the last class, that this is due to the thermodynamic theory. We can now express it in this form, where the rate of change of internal energy equals to rate of change of this C into temperature derivative. So, this is also we have seen in the previous class. Now, if there is and this rho h term is due to the heat source in the body. So, if there is no heat source, this will be this, and this comes from the Fourier law of heat conduction. So, that also you have seen in the previous classes. So, finally, the unknowns are these unknowns. So, one of them is temperature, which is additional due to thermoelastic deformation. Now, since we are forming the uncoupled elasticity, so uncoupled elasticity means the heat conduction can be solved in a separately, and the deformation or the Navier's equation of elasticity can be solved separately once we know the temperature change, or the specifically delta T. So, this delta T is T minus T0. T0 is the initial temperature and T is the increase in temperature, and this increase in temperature T in terms of x and y and z will be specified to you. So, this becomes an input to the thermoelastic system, thermoelastic problem. So, now here we will consider some simple cases, like in the previous purely elastic deformation, where we have considered plane stress, plane strain case. So, in a plane strain case, we know what is called plane strain by now. So, this is this will be epsilon. So, this will be epsilon. So, here we know what is the meaning of plane stress. So, this is a long body in a z direction. So, we know that epsilon zz is 0, epsilon xz and epsilon yz is 0, yz is also 0, but sigma zz is not 0, that we know from the plane stress assumption, and also the W deformation is also considered as a 0. So, now this case what we can write is the displacement field. So, the displacement field I can write in terms of x and y term, and then this displacement field is this u is a function of x y, v is a function of x y, and w is 0. So, our usual strain field will be this. So, del u del x is my epsilon xx, del v del y is epsilon yy, and epsilon xy is the engineering shear strain is half of del u del y del v dx, and these are the plane stress assumption. Now, similar to that, if I now do the stress field. So, just I have to substitute to the Duhamel-Newman relation. If I substitute, so then this is my first Lamé constant and this is my second Lamé constant. So, lambda into this del u del x plus del u del v del y, essentially epsilon xx plus epsilon yy, and then 2 mu del u del x, and then alpha 3 lambda plus 2 mu into t minus t0, similarly sigma yy, and sigma zz for a plane strain is not 0 due to the Poisson's effect. So, this term will be there, and this is the the sigma xy is the shear stress, which is in terms of shear stress del u del y plus del v del x. So, now in a plane strain strain formulation, we will see the equilibrium equation. So, equilibrium equation again we know which is our basic Navier's equation of elasticity, which is del dot sigma divergence of sigma equals to 0 for a static case if we do not consider the body force. So, that is del dot sigma equals to 0 if there is no body force. Now, this quantity for a two-dimensional body, we know del sigma xx by del x plus del sigma xy by del y and so on. So, the equilibrium equation we can write in terms of displacements from the previous this thing, because we know the expression of stresses in terms of strains, and then strains we can substitute the displacements, the expression of strains through the strain displacement relation. We can substitute this in the stress relation, and then substitute, take the derivative. So, this is the final form of the equilibrium equation, this equation in terms of displacement. The important thing is here you see that del T del x and del T del y appears here, that is temperature as a function of xy. So, here T is actually a function of xy. So, del T del x, that is temperature distribution within the body, will be space dependent. So, this can be this appear. Now, since we are following the uncoupled elasticity, that is T is known to us. So, this will act as a body force in the system, because you see T is known to you, and T once it is known to you, this will act as a body force in the system. So, in a thermoelastic case, even if you are following uncoupled thermoelasticity, even if you do not have the body force explicit body force, thermoelastic deformation will due to this thermal change in temperature, that is T, since T is a variable here. So, variable means it is spatially varying. So, that means it is not constant. So, these quantities will be non-zero. So, that means this will give you additional body force. Now, the compatibility equation already we know for a elastic case, which is this. Now, this can be easily seen that if I write these epsilons in terms of stresses, so there is this term is the compatibility equation for the purely elastic or the mechanical case, that is del square by del x square plus del square del y square sigma xx plus sigma yy equals to 0. This is my the compatibility equation for purely mechanical case. Now, if we have the thermoelastic case, if you remember, we were also discussing this compatibility equation when you have a body force, explicit body force in the body. So, if you remember that, then if you can easily derive this, or you can just substitute this can be this extra term will be there in case of a purely thermoelastic uncoupled thermoelastic deformation. Now, this can be this epsilon, since we know the epsilon, so this can also be written in terms of thermal strain, which can be I can show you in a detailed manner. For instance, if you have this del squared epsilon xx del square del y squared plus del squared epsilon yy by del x squared equals to 2 del squared epsilon xy into del x del y. Now, epsilon is actually your epsilon elastic strain or the mechanical strain, and the thermal strain epsilon th. So, I can just extend it to this in this form. So, final the form will be del squared epsilon x epsilon mechanical xx del y squared plus del squared epsilon y mechanical by del x squared plus or minus 2 del squared epsilon m xy del x xy del x del y will be minus this quantity del squared epsilon thermal del y squared plus del squared epsilon thermal by del x squared minus 2 del squared epsilon thermal by del x del y. So, this is epsilon xx, epsilon yy and this is epsilon xy. So, now this equation you can modify if we know the thermal strain. For instance, thermal strain we know that is epsilon thermal T is your alpha delta T. So, alpha is your you know that alpha you know, and so epsilon, and this is delta ij. So, that means this quantity will be 0, this quantity will be 0 finally. So, this is the compatibility equation in the thermal range. Now, this we can finally convert this thing into stresses, and then stress we can write the compatibility equation in terms of stresses, and this is the final form of the compatibility equation. Now, here we have followed stress function approach in case of a plane stress problem, and then also we can form the displacement function approach or displacement potential approach in the plane stress problem. For instance, if I now assume that displacement potential, so for instance, this displacement potential, if I now write that my displacement potential is u is del u del x. So, I consider a function del psi which is a function of x y. So, which I am calling as similar to the stress function. This I am considering the displacement potential, and now this psi, if I now assume that my u is actually del psi by del x and v is my del psi by del y, then my displacement potential I can write in terms of E1 and E2 are the basis vectors in Cartesian coordinate system. So, this is essentially u and v. So, essentially u is u1 and u2, or u v. So, these are the thing. Now, if I use this form, then I get the equilibrium equation already we have seen in terms of displacement. So, mu into del square u plus these quantities. So, u is essentially your del psi del x. So, I will now finally after some rearrangement I will substitute this psi, this capital psi here. So, here if I substitute this psi, so my del square u by del x square plus del square u by del I square will be just second derivative of this psi. So, del square psi by del x square and so on. So, del x of that, and then lambda plus mu is del x of this quantity, and then this is my equilibrium equation. So, now if I write it in a proper manner, then I can simply write it, this quantity is actually lambda plus mu. I can write it here and then I can arrive this form. So, where this lambda and mu is my first Lamech constant. So, now once we know the displacement potential, we can solve this problem, we can solve this equation to get the similar thing that we have solved the for stress function approach. So, finally, this is the second equation. In the second equation again we can have this form. So, this is so del t del y will be there. So, that is the change, and then this will be del square v, and then after some rearrangement I put the definition of psi, that is I write as u as del psi. So, psi of x comma y, and then del psi by del x, and then v is your del psi by del y. So, if I just now put this, then I will have the similar to this form. So, after some modification or manipulation, I can write the final form. So, my two equation, essentially this is converted into this. So, if you write it in terms of E and nu, this Lamech constant we know in terms of E and nu. So, this quantity can be achieved. So, this is my the final form, these two equation. In the previous slide we have seen this equation, and this slide is this equation. So, this is my the displacement function form of the this equation. Now, if I now write it in a if you see that these both the equation is actually very simple. So, I can integrate both these two equation, and after integration I will have a single equation, which is del square psi equals to 1 minus nu by 1 minus nu 1 plus nu by 1 minus nu alpha t. So, this integration, this is a function of x. So, this the constant will be function of y, and then similarly function of x. So, I can this I left to you, because we have seen several integrations in this course. So, this I left to you, and this will be the final form of this thing. This you can derive very easily. You just integrate it and you get this expression. Now, you see this is a very simple equation. So, del square psi, you know what is del square. So, it is a Laplacian operator. So, this thing with the this 1 plus nu by 1 minus nu alpha t. T is your temperature. This is, so this is a Poisson's equation, which we get from the displacement potential function. So, psi is a displacement potential function. If we know psi, we can just take the derivative of psi and then get the displacement u and v. So, the main advantage of this formulation is you basically arrive a single equation. Instead of two equation, you end up with a one Poisson's equation, and this Poisson's equation, once you know the solution, you essentially find out the displacement u and v. But displacement u and v has a specific form where the psi is a function of xy. So psi is a function of xy, but displacement u is actually del psi by del x, and displacement v is del psi by del y. So this specific form we have to be followed. Now, to follow this, actually you need to satisfy the boundary conditions also. So without boundary condition you cannot construct this potential function psi. So that we will see when we will solve some of the examples. So now this can be finally summarized. So this is a Poisson's equation. So in a general Poisson's equation you have two type means once I have a partial differential equation, you have generally particular solution and the homogeneous solution. So homogeneous solution, you know how to find out the homogeneous solution. You put the right hand side 0 and then find out what is the homogeneous solution, and then with the you introduce the right hand side and find out the what is the your particular solution, and the total solution will be a homogeneous solution plus particular solution. But the important thing here is if you look carefully that there is a if you use displacement potential function, so you can essentially convert a single equation which is essentially a Poisson's equation with a right hand side or force vector which is essentially the thermal part due to the thermal part. So T is a function of xy now. So this equation with the boundary condition we can solve for the general solution with the help of particular solution and homogeneous solution. So this is one approach of solving the thermoelastic problem, or this approach is mostly the analytical approach, but analytical approach may not be useful for all problems that we face in our system or society. So we must follow the numerical approach, and numerical approach we can use the finite element, finite difference, or mesh free methods. All those methods we can use to find out the even Fourier series we can sometimes use to semi-analytical approach. Fourier series also we can use to find out the solution of such system. So the today's lecture we summarize this. So we have seen what are the plane strain condition will lead to what are the differential equations in terms of displacements, what are the equilibrium equation in terms of displacement, and what are the Duhamel-Newman constitutive relation in terms of constitutive relation and compliance relation we have seen, and then what is the compatibility equation. The compatibility equation will have a specific right hand side due to the thermal component. Then what we have done, we have just introduced the displacement potential function, so which is essentially psi here, and this psi is essentially del u del x, and this u is actually del psi del x, and v is essentially del psi del y. Now once we put this form into the displacement form of the equilibrium equation, we arrive a single equation for two separate equation by integrating it, because we are solving a two-dimensional plane strain problem. So you have two equilibrium equation. So once you write in terms of displacement of those two equilibrium equation, and then you substitute this displacement potential function, then you arrive finally, after integration, arrive finally a single differential equation or a single partial differential equation or two-dimensional equation, which is this. So which is essentially a Poisson's equation with the right hand side, and then the solution of this system with the boundary condition is particular solution and homogeneous solution. So you know from your basic engineering mathematics how to solve these equations. So we will solve some problem and we will show how it we can solve some problems of practical interest. So I stop here today, and in the next class actually we will consider the plane stress case. Thank you.